So from today, we're going to talk about the line and surface integral. So we have 2 more weeks to finish our semester. Okay, so here, let's start from the definition of a curve. So in the video on Monday, I briefly explained the meaning of a curve, but let me do it again. So when we say a parametric curve, what we mean by that is we have a map called C from interval to some n-dimensional space. And it's so when you say curve, it's a set of points. Basically, it's a line, right? So, but sometimes we say curve to be a function that gives you the image, which is a curve. So we're going to use the word curve to mean both of these. Either it's a function or it's a set. So whenever we have a curve, then we also impose some property that C is always differentiable, which means that if I write the complete formula of my um, coordinates in Rn, let's say it's a two-dimensional curve, then it's xt, yt, or it could be three-dimensional curve, and you have xt, yt, zt, which are the coordinates or formula of the coordinates in terms of parameter t, which lies on the interval ab. Then we assume that this x t and yt and zt, if that's the case, are differentiable on the every points on the domain, on the interval. So once we have this, let's define the line integral. Let f, so this f is, so let me write it this way. So if f is multivariable function and is a function defined on the line, on the curve C. So you can think about it this way. So either the function is only defined on the point lying on the curve, or the function is defined on a small rectangular domain, and there is a curve properly inside of the rectangular domain. So either is fine. So usually when we say line integral, our setting is that we have a function in the formula in terms of the coordinates of the space. So I wrote this way. So let's this be a function defined on C. The line integral is defined to be, so the first thing is the notation C, F, D, S. So as for, same as for the integral, definite integral symbol, this whole thing is just one symbol, okay, just the one symbol here, is defined to be A to B, F, C, T, C prime T, absolute value, dt. Okay? So again, here we assume that our curve C is not just the set, it also comes with the parametric equation of this form, xt or yt, if it's the two-dimensional. If it's three-dimensional, then it's x, y, z. And depending on the dimension where the curve lies in, your function has to have the same number of independent variable, which means that the domain has to be the same dimensional space. So the left-hand side is the notation which indicates a number, and on the right-hand side, you see that's the just definite integral of single variable function. Fct is a function of t, and c prime t is a vector, but we took the norm of that vector, so it's a number. So it's also the number function in terms of t. So we multiply these two functions in terms of t to get the function, single variable function in terms of t. So we take the integration, definite integration, on that interval where the curve is defined, a to b, to get a number. So what does that mean? The meaning of, let's see, the meaning of the line integral c f ds. By the way, this s is a small s because we're going to use big S when we define surface integral. So FDS is the area under the graph of set F over, oh, so let me write this way. So if F is defined on two-dimensional space and C is two-dimensional curve, A to B to R2, then this line integral is the area under the graph of z equals to f of xy on over the curve C. So area, it's the area. The same idea as we define the definite integral to be area under the graph of a function on two-dimensional plane. The only difference is our curve is now two-dimensional curve instead of one-dimensional curve with like interval. So here's the picture. So we have x, y curve, and the curve is lying on entire surface, entire xy plane. But let's put the rectangular box around the circle and think about the graph over that in rectangular box like this. And if you think about the section of the graph by cutting by the line, the curve C, then there should be some figure like this. And there is a section under the graph. So this area is the line integral. Okay. So why is that? It's obvious from the definition. So what we are taking an integral with. So we are taking the value of the function and multiply it with something here, the norm of a vector, and multiply with dt. So if you think about this norm of a vector, so c prime t is a vector of movement on the point, on the curve. So ct gives you the movement of a point on the curve within the time range from A to B. So c prime t is the instant velocity. If you take the norm of a velocity, it's a speed. Right? So you get the speed and multiply with the small increment of time, which is just time. So velocity or the speed times time gives the distance. So these whole two things multiplied gives you the small distance moved by point on the curve. So it's a small width along the curve, along the curve. And you multiply with the value of function at that point, which gives the height. So the width times height is the area of a thin slice of this section, and you integrate from the beginning to the end. You give you sum all the area of a thin slice under the graph, and you take the limit so that you actually get the entire area under that graph. So it's a sectional area. So let me give an example. So here, let's see, the curve CT is t squared, where t is from 0 to 1. So basically, it's a function from 0, 1 interval to R2 with this xt and yt, and xy to be x plus y. So how does this graph look like? So if you want to draw the graph of this function, so here x and y and z, so basically it's kind of these, it's coming out from the blackboard here, kind of. So this is the graph of the function. But we want to find the line integral of this function over this curve. So let's find the value and then think about the meaning. Go for the definition if you want the value. So we have a, b to be 0 and 1. And the first thing we have is the value of function in terms of t, not xy, because we are moving our point along the curve C with the parameter t. So instead of x and y, this is your x, this is your y. Your x and y is not changing arbitrarily. It's always changing along the curve. So you have to use this coordinate function. So t plus t squared is your function at ct. And what do you multiply next? C prime t. So we first find C prime, which is what? 1, comma 2t. It's simply the velocity of x coordinate, velocity of y coordinate, taking a derivative. And we take the norm of this vector. What is it? Right? I can't think of any integration technique to get the exact answer, but uh, this is a function which is continuous on the domain 0 to 1. So you can find the definite integral by approximation. So there is a value. There's some value. So let's think about whatever that value is. Think about the meaning. What does it mean? So I said this line integral is the area under the graph of the function. So we have a graph of a function. So it's not entire, it's not volume, okay? So it's area. So which means that our base is not a two-dimensional region, it's a one-dimensional curve. So here the curve is the parabolic curve because it has t comma t squared as a parametric equation. So we also, it's not an infinite curve. It only have 0 to 1. So it has a start and end. So we are looking at these kind of curve. Maybe the opposite, this way. So it's kind of this way. So the section, this is the section of the graph of z equals x plus y over this parabolic curve from 0 to 1. So so this value, whatever that is the area of these round surface or kind of section. So it's not flat, it's not rectangular, it's a curved surface, right? Sitting vertically on xy plane. The value is the area of that section. Make sense? Okay. So let's think about surface integral. Any questions, by the way? So what is parametric surface? So we have seen the surface many times. For example, torus, or we saw helicoid. We also saw the graph of a surface of a graph of a two-dimensional function. They are all surface. But we want to talk about how to parameterize the surface. So I'm gonna name the parameterization S, and this S is a function from two-dimensional region, rectangular region, to Rn. So usually we assume Rn to be bigger than 3, and mostly we only assume that n to be exactly 3, because if n is 4 or 5, we cannot draw the graph. So we usually just take Sn to be 3 when you say surface. So it's a surface lying on three-dimensional space. And think again. So let's say n is 3, and we have how many parameter here? So parameter is the variable of the domain. So there are two-dimensional, these are two-dimensional domains, so we need two variables. So these variables are called parameters, just like the t was the parameter of the parametric curve. I'm gonna call u and v to be the parameter of the parametric surface. And if I assume n to be 3, this parameter u and v determines the coordinate x and y and z. So whenever you write your parametric surface in terms of two parameters, it doesn't have to be u and v. I'm just using u and v as a common symbol. And you have some formula, three different formula. Then this three formula gives you x and y and z coordinate accordingly. And what happens is, okay, so you have multivariable function. It's a 2 to 3 function. So I'm gonna define SU, so it's just a notation, SU, U as a subscript, as kind of a vector whose coordinates are XU, YU, and ZU. And as V, so it's vector, so let me write down the arrow symbol here, and xv, yv, and zv. So I'm going just notation. I'm just defining new vector or method of finding a new vector out of this parametric surface. So this is my definition. I'm going to use it when I introduce the surface integral of a vector field later. So let me define the surface integral here. So let's say my function is defined on n-dimensional space where the dimension is the same as the dimension of the surface. And as same for the parametric curve, when I say parametric surface, I sometimes think about this as a set, which has a surface on 3 dimension, or I can, meaning that this is a function. So in this case, I'm using the surface as to be a kind of a set, which has a parametric equation. And the surface integral is denoted as S, F, D, S. So here, S is big S, and S is a surface. So there are different S, but not as a symbol, but meanings are different. And this is defined to be the integral, double integral on the rectangular domain A, B, C, D, F, S, U, V times SU cross SV du dv. Yeah, I need SU and SV for the surface integral for the function too. So think about, again, it's the same, similar to line integral. Our left symbol is just the whole thing, just one thing here to indicate a number given by the number of the value of the double integration on u and v. So here, the integrand is everything in terms of u and v. So here, what does it mean? This SUV gives you coordinate of x, y, z. This x, y, z is put it into the function f, which is a function x, y, z. And it gives you the value, the real number value here. And you multiply that value to the norm of a vector obtained by cross product of these two vectors, SU and SV. And then you multiply it. You multiply them. So let me think about the meaning of this. So here maybe I can just think about this n to be always 3. So from now on, 3 here. So the remark, the surface integral of a function is the mass of S, where F is the density. So you have seen this one before, right? You have seen similar statement before. When we talk about the meaning of triple integral, the only way we can make sense of triple integral without using 4 dimension is using the density and mass notation. So here we do the same. We have a surface, okay, we kind of surface, whatever. And let's say at every point on the surface, you have, let's say, x, y, z coordinate, and the function x, y, z gives you the density at that point. So we call this point density. And the surface integral, the value of surface integral, is the mass of the surface in 3 dimension. If you think about this f as a density. Why is that? So let's think about this remark. So whenever you have a point, think about this one first. Whenever you have a point, this point is coming from point u comma v inside your domain, right? So this is your domain A, B, C, D here, A, B, C, D right here. So this mapping is called S, parametric surface. So your point is always one-to-one correspondence between the 3-dimensional point and 2-dimensional point. Now, if you compute your value of function at here, then you map this 2-dimensional point to 3-dimensional point here, and then you take the value of function here. So basically, it's same as taking the density at this point. So you're multiplying density with something here, So what is this? So you have first SU and SV. We need to think about the meaning of SU and SV. So let me draw the picture. This is UV plane. Here you have U and V, and you have surface, our parametric surface, that maps to X, Y, Z. Now, SU, let me write it again, has 3 coordinates, XU, YU, and ZU. Think about XU. It's the rate, instant rate of change of X coordinate when UV is moving in U direction with the speed 1. Okay, think about the meaning of a partial derivative again. So what is the meaning of partial derivative? You want to change the one coordinate, one variable of your independent variable, and you want to move it, you want to change it with the unit speed, and there will be the change of output variable, and you just take a value of x, and then you see how fast does that variable changes. That's xu. So your u is moving in this direction with 1, 0, but then this point is moving all 3 direction. But if you just measure your x direction speed, that's your xu. Your y direction speed, your z direction speed, all that combined to make this vector. So this is SU. Okay? And same thing for V. If you move your point in 0, 1 direction, then you have certain direction of movement of your output point, right? So what is this cross product? What do you get when you get the cross product? I think we talked about this in chapter 2. So when you take a cross product of 2 3-dimensional vector, you get a vector which has perpendicular direction to both of these vectors, right? But here we actually don't care about the vector. We only want to get size of the vector, size of the cross product. What's the size of a cross product between 2 vectors? What does it mean? I think you learned in high school, right? The cross product gives you the perpendicular vector. What is the size of the cross product mean? Area above? Yeah, parallelogram, yes. So you have parallelogram bounded by these 2 vectors. The area is the size of cross product. Okay? So you're making a size, and multiply with the value of function, and you actually multiply with the UDV. So if you take the vector SU and SV, they are big vectors. But what we really want is we want to take a small area at every point, the S here, small area, and then multiply with that area the density, and then get the small mass of the small area, and then sum them up to get the total mass. But here, if you just take the cross product and they get the norm, it's a big mass. I mean, it's a big vector, so you always have some certain um, you have a certain length of a vector whenever you move in certain distance. So it's because we assume that the u is actually moved in 1 unit of length. If you were moving in 1 unit of length, this point x, y, z has to be moved approximately this much or that much if you move in this direction, right? So we don't want that. We actually don't want to move your uv in this much. So we actually multiply with du and dv. I only want to make change, small change in u direction and v direction. So basically, if I multiply that, then I have du, dv. So we get the area of these two small vectors as the size of a cross product times du dv. So the whole thing here is the small area around xyz, which is ds. And I multiply the density to get the small mass, and I take the integration to get the total mass. So basically, that's the idea. So again, let me summarize this figure. So here we have S, F, D, S. So this is the density at X, Y, Z, which corresponds to U, comma, V. And this ds is the small area at around X, Y, Z, which can be approximated by SU, SV cross product, or basically SU du cross SV dv cross product. But du and dv are constant, so I can take them outside. So these comes out outside. Basically, I have cross product of these two vectors. So what is these vectors? So these vector is the small increment or small change of x, y, z position when uv is moved by du, comma 0. So if u is changed by du, then xyz has to be changed its position a small bit. And this is how much the xyz is changed, how much to change the position. And same thing for here. So basically, this is the area, small area, or area of parallelogram. And whenever you have a surface, your surface can be approximated by the set of small parallelogram. Basically, that's the definition of smooth surface, but let's not go deeper into this. So whenever you have approximation of surface with small parallelogram, you can approximate the entire area of a surface as the sum of area of a parallelogram. So it's okay to take the small area of a parallelogram, multiply with the density to get the entire mass. Okay, so that's the idea here. Any questions? Oh, let me give an example here. So let's here. So here let's think about this case. My parametric surface is given by the sphere. So let's think about sphere and how to parameterize sphere. I think in physics class you have spherical coordinate. I think I mentioned in the class sometimes. So spherical coordinate, think about spherical coordinate. So we have sine u cosine v as an x coordinate, sine u sine v as y coordinate, and cosine u as a z coordinate. So this means that we have x, y, z here, and u is the angle between the z-axis and the point. And if I project it down here, then angle between the projection line and positive x-axis is v. So the radius of this sphere is 1. Okay, let's not erase this. So let's compute the surface integral on that surface of constant function. So what if my function, three-dimensional function, three-variable function, is constant? So let's say f, x, y, z is just 1. Okay, no matter what x, y, z is 1. So then let's integrate ds. Okay, so first of all, I need a domain of this parameterization. So what is the domain? So if I want to sweep around the sphere only once, then u can only change from 0 to pi. So u is from 0 to pi. And if I also want to sweep once, then my v has to be round the surface once. So we have v range from 0 to 2 pi, right? So let's think about SU and SV. What is SU? Let's take the differentiation, partial differentiation here. So cosine U, cosine V, and cosine U sine V minus sine U. Okay. So how about SV? Sine U minus sine V and sine U cosine V minus 0. Okay. So let's take a cross product of these three-dimensional vectors. So SU cross SV. So you have to think about the determinant of 3 by 3 matrix, right? Let's assume that there is ijk vector. I means 1, 0, 0, 1, 0, 0, and j means 0, 1, 0, and k means 0, 0, 1, right? And then assume that since we have an order of cross product in SU and SV, this is the right row of the 3 by 3 matrix. What is the i's coordinates, the first coordinate of this? So it's whatever that multiplied with the vector I. So here, if I have a diagonal, then it's 0. If off diagonal, we have these two multiplied. So we get minus s sine square u cosine v. How about j? Okay, so j, I get this positive by multiplying these two, right? So we have sine square u sine v. Okay, so if I have 0, then it's 0. So how about k? So k, I get these positive and this negative. So you get cosine u sine u cosine v square plus cosine u sine v square. So cosine v square sine v square cancel to be 1. So we have just cosine u sine u. In fact, we need a vector, but we have to find the coordinate of three-dimensional vector to get the norm of that vector. So we found x, y, z. This will be used later when I talk about the surface integral of a vector field. But first, here we only need the size of this vector. So what is it? So you take the square root of sum of squares. So if you take the sum here, it's a sine square plus cosine square. So you get the sine fourth. And how about this? We have what? um, cosine square u sine square u. So can you simplify this? So you have sine square u times sine square plus cosine square, which is 1. So it's basically sine square u. So therefore, sine u. So u is from 0 to pi. So sine is always positive in that range. So we don't need to worry about whether or not putting minus here, always positive. So let's go back here. Um, we have function f to be always 1, and our norm is sine u and du dv. And where do we multiply? Where do we integrate? So we are integrating over the rectangular domain, this. And if you want to find this domain, I mean this definite integral, double integral, you either go for the definition using a limit or using Fubini theorem. Let's use Fubini theorem. So I'm going to separate it into two iterated integral, du, dv order. So if you want to integrate first on du, you go for the range of u from 0 to pi. And then your integrand is the same as sine u. And then you integrate over v, so which is 0 to 2 pi. So what is the integration of sine from 0 to pi? Is it 1? Is it 1? Is it, I think it's 2, but is it 1? 0 to pi. Oh, well, let's do it. So 0 to pi minus cosine u 0 pi dv, right? So cosine pi is minus 1, the plus 1, and minus minus 1, so it's 2, right? So it's 2 times 0 to pi dv, and this is 4 pi, okay? So you can say that if the density of the sphere is constant, 1, then the total mass of the sphere, not the ball, it's the sphere. It's two-dimensional surface, okay? The mass of the sphere is 4 pi. But this also means that the area of a surface is also 4 pi, right? So don't think about the unit of density, then the mass is same as the area. So the area of a sphere of radius 1 is 4 pi. So is that the same thing as you remembered as the formula of the surface area of a sphere? Yeah. So 4 pi, 4r pi, where r is the radius of a sphere, is the area of a surface of a sphere. All right. So any questions about this? Okay, so here, um, I need to go to toilet, so I'm giving you an example here. So sorry for that. Let me give an example so you can think about this, and then when I get back, let's do it together. So another example, let's say S is the sphere x minus 1, oh, sorry, yeah, x square plus y square plus z square equals to, let's say, 4. And let's think about x squared plus y minus 1 squared, z minus 2 squared. ds. Let's see. 4, 5, 2. No, I think I need to be a little bit bigger. So Let me think of this again. So we have 0, 1, 2. Size is to be square root of 5. Square root of 5. So let's say 7 here. Square root of 7. All right. It doesn't matter. I mean, as long as um, the inequality. So think about how to get this integration. What's the meaning of this integration? And let's talk about this for after I get back. So I'll give you about 5 to 10 minutes. Excuse me for a while. Sorry about that. So let's do it. Let's do it together. So anyone thought about this? How to solve this surface integral? Any idea? No? Anyone else? Well, I think you can just plug in the parameterization and just write down the equation and it still solve it. So let's say if I want to parameterize this surface with the radius square root of 7, then it will be just square root of 7 times everything, right? Right? Um, so if I just follow the definition, simply follow the definition, this will be integrating from 0 to pi, 0 to 2 pi of this, where x, y, z are replaced by this formula. So x is sine u cosine v square, and y is sine u sine v minus 1 square, and that is cosine u minus 2 square, and you get square root, and you get the square root, and the multiple of this, right? So we have 7, no, square root of 7 times sine u du dv, okay? It's long but doable, right? But that's okay. That's still fine. Mm. So let's use a clever way of doing this. So let's think about the meaning of this. I mean, before we even try to calculate this. What's the meaning of this double integral? So we have a sphere as a surface. We have a sphere right here. And we are looking at the points on the sphere of radius 7. So here radius is 7. We are looking at the point. And we are integrating, we are summing all the values, multiplying this one and ds. So here ds is the small area around this point. So here we have a small area, ds. And what are we multiplying this ds to? We're multiplying with this. And what is this? It looks like a distance. Distance between x, y, z, and 0, 1, 2, right? Where is 0, 1, 2? So if I say this is my x, this is my y, this is my z, 0, 1, 2, somewhere here, inside the sphere, right? And I'm looking at the distance between this point and x, y, z. So this is my function. So this 0, 1, 2 is fixed. My function is the distance measured from this fixed point to any point on the sphere. Oh, by the way, so it's not, yeah, it's the distance, right? Yes, it's distance, right? So I'm doing this for every point on the sphere. So distance not only from this point to this point or that point, but everything at every point, right? So now I wonder, since sphere is symmetric, this fixed point, 0, 1, 2, doesn't have to be at this point, because if I rotate my sphere, it's still the same sphere. If I rotate it with the fixed center, which is the origin, I get the same sphere. And what I'm doing here is I fix a point and just taking the distance from that fixed point to the point on the sphere. So what if I just rotate everything so that 0, 1, 2 lies on the axis of z? Just rotate the sphere. So then my whole picture looks like this. My fixed point is now lying on the z-axis, 0, 0, square root of 5, right? Because I'm rotating so that my line connecting the origin and 0, 1, 2 lies on the z-axis. So the height will be now square root of 5. And then if I take this point as my fixed point, I'm doing the same thing by taking this surface integral. If I take surface integral of x, y, and z minus square root of 5 square ds on the same sphere, well, the formula is different, but the value must be the same as this, because what I'm doing here is taking the distance and multiply that distance with the small radius, small area of any point on the sphere. Make sense? No? So that's why I brought this example. So, um, so we don't want to solve this integral mechanically. We want to figure out the meaning. I think this example gives a good way of think about the meaning of the integral. So think about it again. So let's say this is kind of a density. Okay, so we're taking a density and multiply with the area to get a small mass. So where do I get the density? Okay, so this definite integral means that the density is proportional to the distance between fixed point 0, 1, 2 to the point on the sphere. Okay, because that's the distance. Okay? So now let's get rid of x, y, z axis. Let's say we don't have x, y, z axis. So do we lose any of the meaning that I just mentioned? So I said the density, the point density on a sphere of radius 7 or square root of 7 is proportional to the distance between fixed point to a point on the sphere. if I don't have any axis information, where I don't know where x-axis and y-axis and z-axis are, do I lose any of this meaning? No, I don't lose it, because fixed point is here. It's not changing its position. It's simply I don't know where x, y, z is, but fixed point is here, and I know how to get the distance between this fixed point and any other point on the sphere, so I can get the distance, and this distance is what gives me the density, because it says it's proportional constant, let's say it's 1. So now, just to think about the sphere without axis, but you have to put your axis on this configuration. Where do you want to put your axis? X, Y, Z axis. So let's put the axis in a best configuration, which gives me the easiest way to compute the definite integral. So instead of having X, Y, Z somewhere off position, I'm going to put my Z axis right on the line joining this point origin, the center of the sphere, and the fixed point. I'm going to put the z-axis here. That's here. So if I put the z-axis here, the height of that point is going to be the length between, the distance between the origin and the point. It's square root of 5. So that's my coordinate. And let's also put x, y, z. You can rotate whatever. So just put somewhere, anywhere else here. And then my fixed point have new coordinate, 0, 0, square root of 5. But now let's not forget the meaning, what we want to get. What we want to get by the original surface integral is the mass of the sphere of radius square root of 7, whose density is proportional to the distance between the fixed point to the point on the sphere, right? If I write down the meaning, what I just said, in the form of surface integral, this is exactly the formula. This is the distance between the fixed point and the point x, y, z on the sphere, and this is the density here, density at that point, and I multiply the small area at that point, which is ds, to get the small mass, and I'm adding all the small mass to get the entire mass. I'm not changing the sphere. I'm not changing the fixed point. I'm just changing the perspective. I'm just changing the coordinate configuration of x, y, z axis. The meaning is the same. Doesn't change the s. It's the same s, because what I did is, so even though I said I put my x, y, z axis again, but what I really did is same as rotating my sphere. Rotate my sphere so that this line is now lying on z axis. So when you rotate your sphere around your center, it's not changing the shape. It's not changing the set at all. It's the same set. So if I moved my sphere into different center, then I should change my equation of S. But I didn't, because it's just the same center. I rotated. So now, what's good about doing this? Well, I think we can use different parameterization to get the actual value of this integration. So here I introduced the spherical coordinate. There's another coordinate system of three-dimensional space called cylindrical coordinate system. So let me use that. The cylindrical coordinate system, think about a point is always lying on a certain cylinder. So S, U, V is now, what is it? UV is R cosine, so sorry, R is R is U. Um, so let me write this way. So T R theta Z here is R cosine zeta, r sine zeta, and z. So basically, it's a three-dimensional space coordinate system, so we need three coordinates in order to map entire point on three-dimensional space. So first two coordinates same as polar coordinate system because it's a cylinder and the height is just the height, which is the z-axis. Now, I want to use this coordinate system to find the parametric equation of the sphere. So how do I do that? The sphere, if you look at carefully, let's say it's on the origin. Whenever you have a z, which is the height determines the radius, right? So the radius r depends on z by this equation. So I'm assuming that this is the radius 1. So if your radius is 7, let's say 7, square root of 7, then this is now 7, okay? So when you have a radius, then your points lying on entire rim of the sphere. So therefore, your S, um, what do you need? You need two parameter, the height z and the angle of your circle. So you have zeta z. You don't need r because it's fixed here by the formula of z. So square root 7 minus z cosine zeta, square root 7 minus z sine zeta, and z. Okay, so that's your parameterization of sphere with the spherical coordinate. Gives you another parameterization here. And then let's try to use this parameterization here. First of all, what's the domain? What's the range of zeta and z? So zeta is ranging from 0 to 2 pi because it's the angle. And how about z? What's the range of z? It's the height. The lowest height is minus square root of 7, just square root of 7. So that's my domain, 0 to 2 pi of, and minus 7, 7 here. And then this is my x, this is my y, this is my z. Let's plug that in here. So x here, we have 7 minus z square, cosine square, plus y square, which is 7 minus z times sine square. So cosine square plus sine square becomes 1. So I just have 7 minus z square. And z is z, so we have z minus square root of 5 square. Yeah, so, okay, so we have ds here. No, not ds, sorry, d zeta, d z, okay? Oh, sorry, so I forgot the cross product, right? So something cross product here, d zeta, d z. So let's find out this cross product. First, we need to figure out the s zeta and sz. So what is s zeta? Minus 7 minus z squared sine zeta and square root 7 minus z squared cosine zeta and 0, right? And how about z? Well, everything is 0 except the last. So basically, if I take the set cross product, what is it? So we have, let's put it this way, 0, 0, 1 here. And I, j, k here. So we have 7 minus z squared cosine zeta. And j is also 7 minus z squared sine zeta. And the k is 0. Okay. So, and I take the norm, what is it? Square sum and square. So square root of 7 minus z squared. So this one is 7 minus z squared. Okay. Now I do. Now what I do? So, I, okay. Let's see. So whatever. So what we have here is a bit simpler than this one. So now remember how long and how complicated this is because it has sine and cosine inside. So instead, we changed our definite integral to the integration on of this, and it turns out that if you want to compute whatever you want is 0. So if I use the iterated integral there, so it's 0 to pi minus square root of 7 and 7 of this polynomial, a square root of polynomial, by the way. So we have z fourth minus, let's see, 13 z square, and what? Oh no, sorry, it's not 13. So it's 7. Um, wait. Oh, so okay. So there's a canceling out, right? Sorry. So I thought it was square here. So what is it? So z square. No, z square is canceled here. So we have minus 2 square root of 5 set and 5 plus 7, which is 12, right? And then 7 minus z square. And we first take the integration by z, and then take the integration by d zeta. So basically, there's no zeta inside. So zeta is just, when you take the integration by zeta, it's everything is constant. So it's 2 pi of minus 7 to 7 of some polynomial dz. It's much simpler. And you can actually get the exact number. I forgot to find the exact number. There's a technique to do it, and it's not very hard. Anyway, so the emphasis is that it's not that you can find the exact answer by this trick. It's not a trick. I want to give you the idea of what the definite integral or what the surface integral is, really is. Okay? So any questions about this? So I hope you really understand this because I think that's contains some essence about the meaning of the definite integral, surface integral. So even if you're not understood right now, just take a time and try to think about this carefully. So let's talk about, so far what we have talked about is line integral and surface integral of a function. This function has always the real value, okay? But now let's talk about the integral of vector field. So what is vector field? So what does physics define? How does physics define vector field? What is the vector field? What is the gravitational field? What is a field in physics? How do you answer the question, what is a field in physics sense? Do you learn the word field in physics? Field, field, magnetic field, gravitational field, electric field. What is field? Okay, so math defines field by this way. So I think you can also use this definition in physical sense. So definition of field, a vector field or just field. In mathematics, field is different meaning. So it's just the vector field um, is a map that sends, so V meaning the symbol of vector field, or sometimes I can write down as f. But f is a function, but I have the arrow symbol on top of this symbol, meaning that it's not just a function, it's a vector field. It's a map from Rn to Rn. Okay, so it's not, what's the difference between the multivariable function whose coordinates, number of coordinates of domain and codomains are the same? The only difference is that when I say vector field, the domain is n-dimensional space, but the codomain is m-dimensional vector field, vector space. So it's a map from point to vector. So now, whenever you're asked by some people, what is the field? What is the vector field? You can answer that it's the map that sends a point to vector. Okay, so you don't have to send the point to vector because you can also think about the vector is attached to the point. So usually when you visualize the field, you put your many arrows on your plane, right? So what does this mean basically? It means that at every point where the arrow starts, this point is moving in that direction. You don't put two different direction arrow at one point, right? Because it doesn't mean anything. Because you want to see, if you put your point on that position, you want to see how the point is moving along the field. So you want to attach one arrow at every point on your plane, and this is what this kind of picture means. And this is coming from the definition of vector field, which is a map that sends a point to a vector, or assign one vector to every point. Okay? And there are many adjectives that you can put on vector field. So you can say a vector field is n-dimensional because it's from n-dimensional space to n-dimensional vector space. And also you can say vector field is differentiable if your coordinate functions are all differentiable. So let's say we have two-dimensional vector fields. Then you get, let's see, um, what's a good notation here? Um, um, let's say A and B. Okay, so two-dimensional point a comma y is mapped onto two-dimensional vector whose coordinates are a and b, where a and b are functions of x and y. Here, a and b are numbers. Basically, they are numbers, and you can also think this as a two-dimensional function whose values are just numbers. Okay, so we say a vector field is differentiable if these functions are differentiables. So there are many adjectives, but we'll just skip that. We want to talk about how to take integration of vector field. So let's define this. A line integral of a vector field f on a curve C. So here, whenever I say curve, it's a parametric curve. And I use the same settings that the curve has domain A to B and its dimension and so on, is the following. So here we have the notation of line integral of the vector field. So this whole thing, just one thing, is one symbol. And then integrate from A to B of f c t inner product c prime t dt. That's a definition. So think about again. So on the left-hand side is just a symbol, but its symbol indicates the meaning of the line integral, but the symbol itself, you cannot break it down into pieces and then took it separately, because it doesn't give you any way of finding or computing the value. So the right-hand side is the definition. You want to do the definite integral of single variable function. So on integrand, look carefully. You have inner product. So this white circle dot is not multiplication. It's not multiplication, and it's inner product between two vectors, the vector f and vector c prime. Okay? So that's the difference between the line integral of a real valued function. Just compare the definition. In the real valued function case, we had no vector. It's just the norm, which is the value. So, and also the multiplication is between two numbers. Here, we're not taking multiplication. We are taking inner product between two vectors. And this f vector is n-dimensional vector, and it's computed at the point CT. So let's say this is my C. And here at the point T, I am at here. And at the point, I'm taking what my function, the vector field, gives. So this is the vector f. And I'm say, so let me exaggerate a little bit here. So let's say this is my f. And I'm also taking the velocity vector of the parametric curve. So velocity vector is the tangent vector direction, the tangent vector, and it's actually instant rate of change. And this, let's say, is the SC prime. So I'm taking these two vectors, F and C prime, and take the inner product. And then what I get is the value. Whenever you take the inner product between two vectors, you get the value. So this value is only depend on t, the parameter t. So it's a one variable function, single variable function. You're integrating single variable function over the interval a to b. Okay, that's it. Okay. And let's see what the meaning of this line integral is. So I think you must learn about this in physics. What is the meaning of line integral of the gravitational field? If you integrate, if you take the line integral on the gravitational field, what do you get? Are you taking electromagnetic class or what? Electromagnetic? You're not taking it? It's not mandatory? But it's not a mandatory class? Physics is not a mandatory class? Okay. So um, let's think about this. We have a vector field and we have a line integral. So let's say this is a force field, whatever the force is. It could be electric force, magnetic force, gravitational force. Let's say this is a force field. This looks like a scientific fiction, but anyway, it's field, vector field. And we have a curve. We have a curve, start to end. And this is the work. The line integral is the work done by the field. What do you mean by work? What is the unit of work? What? Joule. And it's the same unit of energy, right? So when you do the work on an object, what happens to the energy of that object? It changes. Is it so? If you give a work, let's say you push some object, it gains the momentum. It gets acceleration. It gets energy, right? And if you let's say so it's the concept is kind of um, yeah, you need a paradigm shift, and also I need it because I don't think of this this way often. So let's say the object is falling from the sky. So who's doing the work? This object does do the work, or gravitation does the work? Gravitation is doing the work. To what? Gravitation is doing the work to the object, right? But then what happened to the what is it called, the um, potential energy of the object when the object is falling? It decreases. So where does the work go? uh, yes. It's kind of kinetic energy. Yes. Let's say it's It's kind of misleading. So hint here. So let's say it's not moving in acceleration. Let's say it's moving just slowly here. Okay, so it's just only there's a change of potential energy. So gravitation did the work to the object, and did gravitational did the work negative work or positive work? So you have to think about the work is not always the absolute value. Work can be done in negative. So if you do the positive work, it gives you energy, right? If you do the negative work, it loses the energy, okay? So that's why we actually have this inner product. So when I say the work done by the field F, it could be a negative energy. It could be the negative work. So when does does the negative work? Let's say the force field is this way. Okay, so I only need to think about the force field at the curve, at the point on the curve. I don't care about what the force field is outside the curve because I'm only moving along the curve, and that's only my concern. So if in this case, if I move along this direction, the force field is this direction, and my movement is the same direction. It's not exactly same direction, but it's kind of a if you just cut in half, you're not going opposite. You're going in the same side of your plane, right? So every time you're moving in the same direction of the force field, so the line integral, by definition, gives you a positive number. When you take the inner product between two vectors, which is pointing in the same side of a plane, or in other words, in this case, the tangent vector and the force field has the angle less than pi over 2, so it's always get the positive inner product, right? It's not opposite. So you always get the positive number, and you're integrating the positive number multiplied with the increment of t, which is also positive, so we get the positive work, positive number, and you get the positive work. So the force field is doing work here. But what if you're moving opposite? What if you're moving opposite direction? So every time you move, every time you think about the tangent vector, then you take the inner product between two vectors, which points to different side of your plane, then you get the negative value, right? So you get the negative, always the negative value of function, and you integrate the negative value, which means that you get the negative value as a total. So when I say the line integral of a vector field is a work done by the force field, it could be positive or negative, okay? So think about this case. Your vector field is always pointing down. Okay? So you can say that the vector field is kind of a constant function with 0, minus 1. Okay? Now, let's say I have a coordinate, x and y coordinate, and let's say I follow through the curve t square. Okay? And I'm moving my t from 0 to 1, so I'm actually going up. So what is my line integral here? So let's compute the line integral of this vector field, which is pointing down at every point along this curve with this direction. So here, there's a very important concept which is different from the line integral of the real valued function. We need not only the parameterization, we need a direction of parameterization. So here, I'm taking the direction to be from this point to that point, start and end. I need to fix the start and end. So let's compute this. By definition, by plugging values here, so f vector field is just 0, minus 1, doesn't matter what xy is, but c prime matters. C prime is 1, comma 2t and dt. So what is it? 0, 1 minus 2t dt, and this is minus 1. So the vector field has done negative work, -1 work, unit of work. So now let's try to go opposite direction. What if the point is moving in the opposite direction? So then what does it change? What is changing? So let's say this was the time t equals to 0, and this was time equals to 1. How do you parameterize this? So the x-coordinate is 1 minus t, because it starts from 1 to 0. When t equals to 0, I need x-coordinate to be 1, and t equals to 1, I need x-coordinate to be 0, so that's my x. And what is y? Y is always governed by the graph y equals to x squared, so it's 1 minus t squared. So that's my new parameterization, where t is still from 0 to 1, but it's now moving in an opposite direction. So let's use this curve. Although the curve itself is the same, but parameterization is changed. So let's see what happens in this case. So here we have 0 to 1, the same range, but the formula of x and y are now different. So it's 0 minus 1, which is f vector field, times c prime minus 1, 2, 1 minus t minus 1 by the chain rule. Let's take the inner product. What do we get? dt 0, 1. I don't care about this. I care about this. So we have 2, 1 minus t dt. So we have 2t minus t squared from 0, 1. When I plug in 1, it's 1. When I plug in 0, it's 0. So it's 1. So compared with the opposite previous case. So if you go up, we get work minus work done by the vector field. If we get down, in the same direction as the vector field, then we get the plus work. So the vector field is actually doing work here, but the work done in the opposite direction is the negative work. The same amount, but negative work. Okay? So we are not talking about the work done by the object. It's the vector field which does the work. Okay? So yeah, so I think it takes a while. I mean, I heard this kind of perspective of interpreting the line integral as the work done by the vector field from the professor in physics professor who were used to be here in DGIST. And after I heard this kind of perspective, it kind of changed the way I look at the physics. So I hope you can think about this also in the same um, I try to think about this, the meaning of work done by the vector field. So I think we are too used to think about the work is work is all the time. So somehow there is a person or there is an object which actually does the work, but it's not really the object or person does the work. It's the field that does the work, right? It's the field. So anyway, there are two properties. I'm probably finished by now. So um, line integral is defined to be this way. And the important thing is when you even state the line integral, you have to provide the direction of your curve, your direction of the parameterization. Because if you switch the direction, the answer gets opposite sign. Okay, so that's the only thing you have to worry about. And another thing that I can mention is that, okay, so what if I have the same curve? What if I have the same curve but different parameterization? So for example, what if I take ct to be t squared t fourth? Instead of tt squared, I get t squared comma t fourth. It follows the same curve but in different velocity, right? Every time I move in this case, 1, 0, in the x direction, I always get the unit speed. But here, the speed of x direction is changing by time, right? So my question is, what if I change the parameterization? Would the line integral change? And the answer is no. The line integral, the final line integral value is not changing by changing the way we parameterize. As long as this curve is the same, it doesn't depend on the way we parameterize the curve. But again, it depends on the direction of parameterization for this line integral. But don't confuse with the line integral of a function when we have this thing. Here, we had the norm, right? This C prime t could be either direction to get the same norm. So in the line integration of the real valued function, the parameterization direction does not matter. It doesn't matter. And by the meaning, that makes sense because it's the area. Whether you take the area from the left or right, you get the same area. But here, we're talking about the work. So therefore, it depends on which direction you're putting the work onto the object. It could be opposite. Okay, so I'll talk about the surface integral next time. And if you have any question, let me know and see you on Monday.